basically talking about an algorithm. So this algorithm here, this one here, is from sklearn. So this algorithm, what it does is it's basically designed to identify anomalies or outliers. So I will be using anomaly and outliers interchangeably because they are basically the same thing. So we are going to train our data to tell the model to identify anomalies or outliers in our data set. By doing that, we will have a high dimension data efficiency. So, and another thing why I like this solution forest is it is an unsupervised learning we are going to do here. What do I mean? The unsupervised learning means it doesn't require labeled training. Like it is, we don't really need labels to train our model. So we are going to be training it using pattern. In this place, I was having some errors about not really error, it's like warning. So that's why I use this error warning filter this to just to suppress the warning messages. So that's just the purpose of this. So I'm taking my IPs from the Wireshark data. This I'm actually loading my raw data. I'm not using the pre-processed data for now. I'm taking out the Wireshark raw data. Then I'm extracting the IP address from it. Then after doing that, I'm saying that okay, now I need to extract the source and the destination port. Uh, while extracting them, I'm using a P series. Actually, this P series is a one-dimensional array-like structure for in pandas. It's usually we use it to represent a single column of data. So it's just that's what the P series means. Here, after loading my Wireshark data, I extract because I already did this before in this place. So I'm redoing it again since I want to train my data. I'm extracting the the time when the data arrived or when the data left. When the data arrived, actually, the source IP, the destination IP, the protocol, the length. Then after doing that, I normalize the all the features that I took. Those features, I'm assuming they are in a string format. So when I normalize them, I'm transforming them to a numerical value. So before doing that, after doing that, I will have to split my data. So uh, the idea behind training of data is if you have data in 100%, you have to split it. Maybe here I'm saying test split of 0.3. 0.3 means 30%, meaning I will be training my model with 70% of the data and 30%, 0.3% of the data will be used for testing. This feature is actually confusing. It says random state, but I actually define it as 42. It means that I'm being, I've, what is it called? I'm fixing uh, the randomness of my model to be 42, meaning no matter the data will be consistent no matter how many times I regenerate the data or I rerun the model, it will be consistent with this value. My result will be consistent actually. So here I have my X train and S test. So here you can see that I'm actually importing this from the model selection. So I'm selecting my data. I train and I test. Here after doing that, I am passing them my taking my isolation tree. Then this is a features from the isolation tree, which is contamination. The contamination is actually a parameter from the isolation tree. It means that the model should expect a proportion of outliers like an anomaly. So here I'm saying 0.1, it means 10%, that I'm assuming the model will be expecting 10% of anomaly and the random stage just to make it fix. Now I fit in my data with the ones I train it with after dividing it here. Then I save my this is an artifact. I save my isolation tree model Wireshark with the scalar. The scalar is just a way of it's a standard it's a way of standardizing my futures. Here I added this recently just to make sure that we just to visualize something on the terminal. At least this is just a way of taking my just to take out the check out my predicted anomalies. Then I converted them to a binary and I do some calculation. I print them out into the console. Uh, since I already have my preprocessed data, let me play this to train the data. So as you can see, I'm generating I actually generated an artifact of isolation forest model and the scalar. So we have this scalar is different from this scalar, but they are very very similar. Then the last part I actually talked about, which is this place, just to check out my anomaly prediction and the values I'm getting. So I'm having an anomaly ratio that a training set of 10.29%. Then the test ratio was 30%. Then the average anomaly score set and the score in test was 0.05. So after training all my data, the next thing is to use the data for to detect an anomaly to see how it works. So you can see that this is the place we are feeding all the trained data into our model and using them. So this part I will let my colleague explain everything we did in this part. Uh, Let me see if I can actually look at the inspection. I could actually, let me quickly, these are the old data. Let me delete this. So let me quickly inspect the data that I actually trained to see if I'm having a. So I'm actually just inspecting the data with what I just had. We can see that this is actually how my data is performing. It is not actually performing very good because this is an outlier. Those are outliers. The data is performing poorly because I trained it with a bare minimum data. We need a huge amount of data, like a day or two data that we generate from here, at least to have a good concentrated data. So this is why the data is not performing very well. This is actually a very poor performance. So my colleague will actually explain the other parts, but this is the future importance. When we standardize the data, we normalize them. You can see that every futures in our model, they are actually in equilibrium. They are all the same. So this is to make sure that no feature of the data is outperforming the other. So so as we can have an accurate result. We have the heat map. I believe my colleague will talk more about the heat map and anomaly distribution in the next slide. Thank you.